Got it? I'll begin with a word of prayer. Dearly Father, we thank you again for this opportunity we have just to meet together and to study your creation. I just pray you be with us today. Help us to glorify you in what we do, Lord. In your name I pray. Amen. Okay, so since I had the projector out, I figure I should just go through a couple of pretty pictures with you for a second before I forget. And then we'll get back to arc length in all of its glory. So, I defined this for you the other day, but I would remind you that if we have a path, right? In other words, a parametrized curve in 2 dimensions, physically speaking, you could think of r of t as being the position at time t. The derivative would be the velocity at time t. And then if you differentiate again, the derivative of the velocity with respect to time is acceleration at time t. Right? So those are easy enough to calculate for all the examples we've looked at, right? You just differentiate once or twice, and there you go. Velocity, acceleration. Here's an example. If I have the path r cosine omega t, r sine omega t, which is, by the way, just r times this vector, cosine, sine. This is a unit vector. It has length 1. It just points in the direction of standard angle omega t. Anyway, calculate the velocity. See, we always have this problem. Whenever people walk on the roof, it makes the projector go woo. So, yeah, it's one of the joys of teaching in here. Anyway, so this, but it does make me sick after a while. I don't know. Anyway, so differentiating pulls an r out, right? It actually pulls an omega out, doesn't it? Differentiate this, you get minus omega sine t, cosine omega cosine t. So I can pull the omega out. There's my velocity. And then my acceleration, differentiate 2 times. I bring out another copy of omega. I get minus signs on both, so I get minus r omega squared, cosine sine like that. So, in other words, the acceleration in this curve is equal to minus omega squared times the position in this very special example. I think I have a picture here. So sometimes it's helpful to actually picture these things. And so this is a circular path, right? And I've just done the math to show you the acceleration vector. So the position vector goes from here out to that point. I haven't pictured it, right? And the acceleration vector points opposite that direction towards the center. And then, of course, the velocity points tangential to the curve, and it just goes round and round and round. And the acceleration vector is always the same length, but always pointing towards the center. That's because we're looking at constant speed circular motion. If you've had physics, you studied this some, right? But here's another. Come on, I am having trouble with this PDF here. Here's another popular example in physics. Suppose the acceleration is just 0 minus g, right? That's this one, right? Like that, In case you didn't see the first one. And so forth. Oh, one more. I'm out. With the. All right. Actually, it would make a really cool splash. But no, I would not do it. All right. You want me to be YouTube famous? Well, that's very thoughtful of you. I do appreciate that. Internet sensation. Yeah. I don't know. Maybe if I say the right politically incorrect thing, but I don't know. But odds are more on that. I mean, in any given lecture, I'll make at least 7 or 8 microaggressions and a few medium-sized ones. So, not a safe space. But, sorry. Anyway. So, if I have the acceleration is 0 minus g, if I integrate, I can get the velocity, right? So, integrate the dv dt and integrate a of tau d tau. That gives me, from the basically fundamental theorem of calculus, v of t minus v of 0. And on the other side, I integrate this. Well, that just gives me 0 minus gt. And there you go. That's the velocity for constant acceleration of minus g down. Integrate again. I get this formula for the position. The position is the initial position plus t times the initial velocity. And then plus this term from the acceleration 0 minus 1/2 gt squared. Now these basically, if you expand these out in the component formulas, you've got x is equal to x naught plus v naught x times t, no acceleration term, and then the y is equal to y naught plus t times v naught y minus 1/2 gt squared. When you take a course in physics, you study these kinematic equations, right? You solve problems with these. You get to know these pretty well. But we can derive those just with a simple calculus derivation like that. Here's a picture of what's going on. So if you do one of these deals, or like this, oops, that's this kind of motion, right? Whatever horizontal component I gave to the velocity just keeps going at that rate, and the acceleration is always downward, minus 9.8 meters per second squared, and that ends up producing a path that looks like this. This is a parabolic path. You can prove that by eliminating time and showing that you get a parabola in y and x, right? It's not immediately obvious that that's a parabolic path, except perhaps you've been told it before. Have you ever proved it, though? Have you ever proved that if you set this equal to x and this equal to y, if you eliminate time, you get a parabola? Because that's what actually would be required to show it's parabolic. I think I broke this marker. I better use it today. All right, so now, a little bit more language here, and then I'll get back to the math. So the displacement from one time to another is called, it's the change in position. So it's a vector. Like my displacement from, say, this time to this time would be the vector which points from there over to here. Displacement is a vector, all right? And it concerns two events. It connects the two events like that. Distance traveled, on the other hand, it's not just the length of the displacement vector. Distance traveled, like, so I could go from here, over to here, and then I could go back. My displacement would be 0, but my distance traveled would be about 12 feet. I don't know, something like that. 16. I can't have no sense. Somewhere between 10 and 20 feet. All right. And so to calculate the distance traveled, you can imagine just laying a string out as you walk and then laying it back. And so that's exactly the arc length of the curve that you went over. So distance traveled, you need to calculate the arc length of the path, which we learned last time is this. All right. I just want to give you one example of arc length, which is pretty non-trivial, and then I'll actually work some examples with numbers in them. This is the arc length function. I'll talk more about that later. See here going on. This is a genuinely difficult. Nope, still not it. Sorry. So here's the. I wanted to calculate the distance traveled by like the marker I just threw. Right? Like how far does it travel? What's the if you laid a string along the parabolic path that goes through the air, how long would that string be? You know? So to do that, I look at the oops, sorry, my laser. I look at the path that it travels, something like this, right? And oh, come on, this is still not the right. I thought I was at the start of the right one. Yeah, oh yes I am. The way it's scrolling is driving me nuts, guys. I'm sorry to be distracted. It's one step forward, two steps back, you know? And there's no opposites or attraction or anything. It's no fun. Let's see here. What is... Whoa. It's not cool. Golly, guys, I'm sorry. You know what? Forget it. I'm tired of Microsoft Edge and its stupidity. Of course, Adobe has its own stupidity. Let's see. Oh, where are we? There we go. Sorry, guys. And see, I don't need, go away, skedaddle. All right, I would like. I'll be content with this. So to calculate the arc length of this parabolic trajectory, I have to calculate the integral of the speed. See, v without the vector is the speed. That's the magnitude of the velocity vector, right? The square root of the x component squared plus the y component squared gives me the speed of the thing. And so the speed of this is that. And so what I do here, I make a u equals to v naught minus gt substitution, which gives me this. Do you guys remember how we integrate this, like a square root of something squared added to something else? Remember what we did? Trig substitution would bring me to like secant cubed, I think, here. We made a hyperbolic substitution, but yeah, right idea. So you make a hyperbolic sinh substitution, and after the hyperbolic sinh substitution, I can do the integral, like so. And so then the integral, I'm missing some, here's the antiderivative, it's just this monstrosity. And so in short, using the fundamental theorem of calculus, I find that the distance traveled by the marker I just threw is 1 over twice gravity, the x component of the marker's velocities to start with squared, inverse hyperbolic sine of the quotient of the y velocity divided by the x velocity, plus the y velocity times the square root of v naught x squared plus v naught y squared. Yeah, so there you go. If you want to figure out how far the marker went through, you just plug it into this. Pretty easy, right? No, I was actually starting this example as I wanted this to be an example of one where you couldn't actually calculate the arc length because the integral was not doable. And then like I got halfway through it, I'm like, oh, I can do the integral. Oh, this is weird. Because I haven't seen this formula like anywhere, but there it is. I will now put this away and show you examples. All right, so. Anyway, there's another page in there for you guys to look at where I discuss tangential versus centripetal acceleration. I think that could potentially be helpful for you as you try to understand physics 231. It's part of the reason I do that in here. So, all right. Let me turn the lights on. So what did we find last time? We found that the definition, if r of t equals to x of t, y of t, for, let's say, t1 less than or equal to t less than or equal to t2, and x and y are both differentiable functions on this interval, then the arc length of that is just defined to be the integral from t1 to t2 of, well, I can write it this way. It's really just the length of dr dt. Now, so I mean, that's a nice definition. If you want me to give you sort of a more hands-on formula for it, let me do that too. What this means is the integral from t1 to t2 of the square root of dx dt squared plus dy dt squared. dt. All right, so that's the arc length formula. The arc length function, by the way, s of t, the arc length function is just defined to be the integral from t1 to tau, let's say, of the square root of dx d tau plus dy d tau squared d tau. This is the arc length function. Based at t equals to t1. So it's really not that complicated a thing I'm talking about. If the path, looks like this, and this is r of t1, the arc length function just says, hey, if you go this far, right, if you go to here, right, and that is r of t, well, guess what? This length of string I just rolled out here is s of t. It's the arc length function. That's all it is. So the total arc length of the curve, right, over here we have s of t2, which I just called s. I mean, it's the total arc length. So let's do an example. Yeah. Unless there's a question. Oh my goodness! Thank you. Yes, I have just committed the sin I was trying to avoid. The whole point of putting tau there is so that I don't have the integration variable be the fixed but arbitrary time we're thinking about, namely t. So, thank you. As usual. Let's see here. Other questions, comments, corrections? Jokes you want to share? No, I should never add that. So here's a very popular example. R of t equals to r cosine t, r sine t, 0 less than or equal to t less than or equal to 2 pi, aka a what? Right? You know it. You love it. It's the circle of radius r, right? Let's calculate its arc length. So, s. In fact, we can calculate its arc length function while we're at it. Let's do that. Based at 0, s of t should be the integral from 0 to t, right? Of the square root of, let's see here. So, let's see here. So we get minus r sine tau squared plus r cosine tau squared, right? D tau here. I'm noticing x of tau is equal to what? R cosine tau. Y of tau is r sine tau. So what happens here? We have sine squared tau plus cosine squared tau, which is otherwise known as? Yeah, that's just 1, right? And then the square root of r squared. Now, what do we assume about r? I should have said at the beginning, but don't be weird. R is 0. R is positive, right? What's your radius? My radius is minus 5. Get out. You're stupid. Sorry. Some of you may have been raised in houses where you're not allowed to say stupid. Now arriving at the university, you find out people say stupid, and you're amazed. Let's see here. Sorry if that's your life story. Let's see here. R. I don't know how many of those sorts of people exist. My uncle is such a person. Let's see here. Like, we don't say stupid in our house. And then I'd be like, that's stupid. Sorry. I think I'm offending the right people, though. I don't know. Yeah. Square. Mm-hmm. The squaring function is the natural enemy of minus 1. It kills it every time. So basically all this calculation shows is that if you go from time 0, which is where? Where's time 0? Time 0 is this point right here, right? and then you go out over here to time t, right? This length of that curve I just drew is s of t. Right? So of course then, what's s of 2 pi? The total arc length, right? 2 pi r. There you go. The circumference of a circle, 2 pi r. But since t is the standard angle, right, we also have a derivation that, some kind of derivation, it's probably circular, sorry, that the arc length subtended by t radians is just r times t, right? That's not particularly surprising, is it? What's the relation between arc length subtended and radians? S equals r theta, right? Here theta is equal to t in this parameterization. That's the geometric meaning of t. T you could identify as being theta. Is there anything else you could say about this example? I mean, something I should make a comment here. This is an important thing to notice. So dr dt is equal to the velocity, and v without the vector on it is defined to be the magnitude of v, all right? So this is the so-called speed. All right, the speed is the magnitude of the velocity. How do you calculate arc length? Would I do something? No? Okay. So the arc length, right, is equal to the integral of the speed, like this. I mean, more to the point, s of t is integral from 0 to t of what? Of v of tau d tau, right? So, another way to package the calculation to calculate the arc length, you take the path, you calculate its speed, then you integrate that over the appropriate range of parameters, that gives you the arc length. When we're calculating the square root of the square root of dx squared, dx dt squared plus dy dt squared, what we're doing is we're finding the formula for the speed. Right? That's what it means. You can get a little bit more here. If you differentiate this with respect to time, what do we get? What's the integral of what's the derivative of an integral with a variable bound? Yeah, v of tau, but we plug in t equals to tau, right? So there you go. I mean, the speed is the infinitesimal change in the arc length with respect to time. Right? So it makes good sense that if we integrate, I mean, once you have this this is circular, right? But all things work together for good, I suppose. Those who know calculus. Let's see here. So that's not how it goes. Let's see here. V dt equal to ds is an infinitesimal sort of principle. Integrate both sides. That's why we get arc length from integrating the speed times time. Okay. Anyway, these are a circle of ideas. Okay. So example 2. Unless there's a question. Okay, I hope this works. I'm not sure. Let x equal to. Oh man, I shouldn't make up. I can. I'll tell you what. I'll do it, and we'll see what happens to us. How about that? Cosine t, and let y equal e to the t sine t, right? So in my other lingo, it says r of t is e to the t cosine t, e to the t sine t, right? What? Oh, it doesn't matter. And let's say this is for t greater than or equal to 0, right? But I want to find the arc length for a specific thing. So let's calculate arc length for t equals to 0 to t equals to, I don't know, 3 part of this curve. Path, say. Do you guys know what this path is? If you think of e to the t is what? It's serving like, think about the previous example. It's like I'm replacing r with e to the t, right? So if you fix r, you get a circle. What happens if you take a circle and then you allow its radius to change? So maybe I start here, right? This is, at t equals to 0, we get what? 1, 0, right? What happens when you get to t equals to pi over 2? Right, cosine of pi over 2 is 0, right? Sine of pi over 2 is 1. E to the pi over 2 is what? What's e to the pi over 2? I don't know right off the top of my head. E to the 1.5 is what? Let's say it's 5. What happens when you get to pi? E to the pi is like e cubed. That's like 27. It's pretty big. Sine of pi is 0. Cosine of pi is minus 1. It's over here, right? And so what you're going to do is your spiral. It's a spiral. It spirals out, right? If I was to draw it different scale, it'd be more like just. That's what we're looking at, the spiral. Okay, so the arc length. So I would say step number 1 is find nicest possible formula for speed. See, I just did it in one file sweeping calculation over here because this one wasn't that bad. But generally speaking, as a point of organization, it's in your best interest to find the formula for the speed first and then integrate it. Because you don't want to be doing algebra carrying the integral sign along, right? I know you guys. You're going to write the integral for like the first 2 steps, and then you're going to stop writing it. And then I'm going to take off points, and then we'll all be sad. So let's just think about how to write correct work, a little bit now. So what's the speed? Well, dx dt is what? What's dy dt? It's e to the t cosine t minus sine t. It's e to the t sine t plus cosine t. Right? Well, I did the product rule and I factored out the e to the t. You'd say, well, why'd you do that? I don't know. It just seemed like a good thing to do. Do I have to explain everything? Like, that's what they pay you for. That's true. I guess that's true. If you have questions, you can ask them. I decided to add extra sarcasm to this lecture since we had CFAWs here. But usually I'm not sarcastic at all. No. Okay, so then to calculate the speed, what are we looking for? Remember, speed is this thing right here, right? This quantity is the speed. So I need to calculate dx dt squared plus dy dt squared and then take the square root. So what's dx dt squared? What's dy dt squared? So when I square that, I get e to the 2t, right? And squaring this gives me cosine squared t minus 2 sine t cosine t. Or if you like cosine sine, whatever floats your boat, plus sine squared t. Right? This is what we should get from squaring the x velocity. Squaring the y velocity gives me e to the 2t, kind of the same thing. Oh, I'm sorry, sine squared t plus 2 sine t cosine t plus cosine squared t. Right. So what happens when we add dx dt squared plus dy dt squared equals to e to the 2t times what? Cosine squared t plus sine squared t plus sine squared t plus cosine squared t plus 2 sine t. I don't know why I'm writing all this out. This really doesn't need to be written, because you could do a little bit of thinking and write less, couldn't you? I mean, I think you're totally within bounds to just go e to the 2t times what? I heard a 2. Yes, 2e to the 2t. Because sine squared plus cosine squared is 1. You got 2 of those, right? And the mixed terms, the sine cosine terms, cancel. Right? So, we have now found, I would argue, the nicest possible formula for the speed. And now we can calculate the arc length. So S is equal to z integral from 0 to 3 of the square root. I mean, this is the speed squared, right? Technically, this is v squared. I didn't take the square root yet, right? So square root of 2 e to the 2t dt. In other words, the square root of 2 times the integral of e to the t dt from 0 to 3, which gives me the square root of 2 times e to the 3 minus 1. Which is kind of neat, because if you look at the spiral, it doesn't seem, I mean, it seems like maybe it's a complicated thing to calculate the arc length, since it's always growing bigger and bigger and faster, and not at some sort of linear rate or anything either, right? I mean, the radius is literally exponential. So, any questions? Something very wonderful happened here, didn't it? The thing under the square root just became a single term, right? And we're even able to just simplify it to an elementary function. This example is special and rare. Usually, if you just go off into the woods and try to calculate the arc length of something, it goes badly for you. Here, let's look at another one. Let's look at y equals to f of x, and let's look at f of x equals to x to the 4th plus 1. All right, so find arc length for 0 less than or equal to x less than or equal to 1. So if we have a graph, how do you convert it to a parametric curve? Basically, we just say, okay, so I'll use r of x equal to x, comma, x to the 4th plus 1. That's my parameterization for a Cartesian curve. Just use x as the parameter, basically, right? So, or if you don't like this, we could say r of t, right, is t, comma, t to the 4th plus 1. I'll stick with the second, just so I can write things that are less disturbing. So x is equal to t, y is equal to t to the 4th plus 1. So what's dx dt? What's dy dt? Dx dt is 1. What's dy dt? 4, you have 4t cubed. So the speed is equal to the square root of 1 plus 4t cubed squared, right? Square root of 1 plus 16 t to the 6th All right, so the arc length is going to be the integral from 0 to 1 of the square root of 1 plus 16 t to the 6th power dt. No. This is just unpleasant. Tell you what, I'm feeling adventurous. Oh, wait a minute. Well, well, yeah. I mean, t is relatively large. I could try to use like a binomial expansion. Yeah, let's try it out. This will probably go badly. So 1 plus u to the 1/2 power is what? 1 plus 1/2 u, right? And now I've forgotten. Is there a plus? Is there a plus? Or I know then it's plus 1/2 times 1/2 minus 1 u squared plus 1/2 times 1/2 minus 1 times 1/2 minus 2 u cubed plus dot 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 dot. Am I remembering this right? Can you guys check me on this? The binomial expansion, we worked this out, remember? I used alpha instead of k, I think, that lecture. I mean, I had a half. I think I had like an alpha. So if I'm right, this is 1 plus 1/2 u minus 1/4 u squared. Let's see here. This is plus 3/8, I think. U cubed plus dot 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 dot. So this is really the integral from 0 to 1 of 1, and we'll have to judge whether or not this is a reasonable substitution in just a second here. 1/2, my u is 16t squared, t to the 6th rather. So minus 1/4. I think this is not a reasonable substitution. I mean, I don't think this is a productive calculation. I'll show you why in just a second here. Well, that's enough. Okay, so what do we have here? We have the integral from 0 to 1 of 1 plus 8 t to the 6th, right? Minus, I think that's 4 times 64, which is, wait a minute, no. 4 times 16, that is 64, yeah. T to the 12th, yeah? And so here's the thing. You do the term-by-term integration. You got yourself a 1 plus 8/7 minus 64 over 13 plus dot 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 dot. So yeah, the thing is, this is not the right kind of. In order for a series calculation to be reasonable and worthwhile, if you're going to truncate it at a few terms, what do you need? You need the things that you're not calculating to do what? Get small, right? What happens to the terms I'm not calculating? Yeah, they're going to get bigger and bigger and bigger. And I guess the question is, well, anyway, bottom line is this is no deal, okay? So how do you do this integral? This is why you might have a question on the test next time where I say, calculate the integral solution of the arc length. And this is what I'm talking about. So if I say that, that means that you find an integral, which if you could do it, gives you the arc length. And this is actually the answer right here. We've reduced the arc length to an integral. That's the integral solution for the arc length. We actually know how to do that. We could use the left endpoint rule, the right endpoint rule, the midpoint rule, Simpson's rule. There's a number of numerical techniques at our disposal. Just because we can't find an antiderivative doesn't mean it's game over. And I mean, although I do think that if I was more clever with series methods, I could find some way to approximate it using other techniques, right? But if I'm going to do that, I have to find a way to expand it in terms of a small quantity, not a large quantity. So anyway, that's something I haven't really taught you guys. No one teaches you in Calc 2, although it's probably the one thing we should teach you. Anyway. Okay. Shh, tell no one. I mean, I don't know. I think this is a productive thing to have done, but, you know, there it is. Let's see if I can find another example for you guys. So some arc lengths you just can't calculate nicely, all right? Here's one that works out actually okay. We'll look at x equals e to the t plus e to the minus t, and y is equal to 5 minus 2t. This is example 4. I mean, I knew this was going to happen, guys. I did that on purpose if you hadn't gathered that. And that's, you know, something you have to be aware of is in the real world, most arc lengths you can't calculate in closed form. It's one of the primary reasons that we want good numerical methods is to approximate integrals like that. Anyway, minus e to the minus t. Let's see here. I guess I should pick a parameter domain, parameter range, let's say. Let's say for 0 less than or equal to t less than or equal to natural log of 2. That seems fun. Find the arc length. So what am I doing? I'm going to calculate the velocity of the x, the velocity of the y. I'm going to find the speed. I'm going to integrate it, and we'll be done with this example. So what's dx dt squared plus dy dt squared? So what do you get when you multiply that out? So here we go. We get e to the 2t, right? Minus 2 e to the t, e to the minus t, right? Plus e to the minus 2t, plus 4, which is also known as e to the 2t, plus 2, plus e to the minus 2t, right? Or, I don't know, maybe it's even better to write it this way. Plus 2 e to the t, e to the minus t, right? See, because that 4 is really just 4 what? Whoa, this marker's dead. E to the t, it had a good life. Oh man, I hate that this marker's cap's broken. Oh, maybe it's just the cap is broken. Maybe let's still save it with another cap. Let's see here. That one's sad. Aha, it lives on. All right. Sorry. Actually, I'm not really that sorry. I'm going to say stupid things like that for the rest of the semester and pretty much any other class you take me with. So anyway, here we go. You see what I did? I've just recognized that that 4 is really the same kind of thing as this. So I've got 4 of them over there. I've got minus 2 of them here. In total, I've got 2. And now we can factor. All of the arc length problems that you can actually calculate in closed form, either they're involving like sine squared plus cosine squared and a conspiracy to add together to 1, something like that, or there's some sort of magical squaring that happens, or it happens to be one of those rare integrals of a root of something that you can actually calculate. These are all rather special events. This is really more what happens in the big scheme of things. But anyway, so this is e to the t plus e to the minus t squared, right? And so that's equal to the speed squared So therefore, the speed is in fact e to the t plus e to the minus 2t, right? And so the integral of the speed from 0 to log 2 would be the integral from 0 to log 2 of e to the t. Why do I have a minus 2t all of a sudden here? Like, why? Why? Why would I write that? Like, just sad. Sad. Okay, anyway, so e to the minus t, yes. E to the t plus e to the minus t dt, you can do the integral. We've got e to the t minus e to the minus t, evaluated from 0 to log 2 by fundamental theorem of calculus part 2. So there you go, that's e log 2 minus e to the minus log 2, and then what, minus parentheses e to the 0 minus e to the 0, of course that's 1. 1 minus 1, which is 0. So we get 2 minus 1/2, which by the way is 3/2. If you don't, what I did there was e to the minus log 2 is what? That's e to the log of 2 to the minus 1, which is 2 to the minus 1, which of course is 1/2. Es bueno? Let me show you 2 more examples from the notes. Once you're, people stop writing. Well, don't stop writing. Keep writing. When you're done writing, I'll bring the screen back down here again. You guys good? Okay. So I think pretty much next Monday we'll start into polar coordinates. All right, and probably, well, either Monday or Tuesday we'll have the quiz. I haven't decided yet, but the quiz will be on this week's material. So you guys, you should think about what is a parametrized curve and think about your questions about them. You guys haven't asked nearly enough questions about these things yet, and they always confuse you guys. So I know you don't understand. I'm being stereotypical, but if you're like almost every other class that's ever taken Calculus 2, you guys don't internalize what a parametrized curve is, Oh man, I was going to do an example today. Curses. Yeah, I'm out of time. So here's one. X log x is equal to the x component's x, the y. Basically this is just the parameterization of y equals log of cosine x. So this alpha, you can make r of t if you like, all right? R vector of t, my usual notation. So here's the speed in square root of 1 plus dy dx squared, but the derivative of log cosine is minus sine over cosine. Well, you square that, you got 1 plus tangent squared. Isn't that convenient? See, this looks kind of scary to start with, but when you calculate the speed, you find out that the speed is secant x. Well, it's not too nice. It's still an integral of secant, but we know that by this substitution. So we get, log of secant plus tangent, which here ends up being log of 1 plus root 2. Again, the actual, our ability to calculate this was based on something inside the square root being nice. You got to look for patterns there, especially like factoring. Here, this next one has the factoring I'm talking about. Oh, not this one. This one just shows you that the circumference of an ellipse, unlike the circumference of a circle, is not something that's nice. Generally speaking, it leads you to this integral, a times the square root of 1 minus beta squared cosine squared t, where beta is, I think, that ugly business right there. So that integral doesn't generally have some nice closed form solution. Like to calculate the arc length of an ellipse, you got to resort to a numerical method for a lot of values. Now, for a specific one, you might find you might be able to do it, but generally speaking, a numerical method's required. This one is kind of a typical, a magic happens example. x cubed over 6 plus 1 over 2x, 1/2 less than x less than 1. So when you differentiate, you get that. You square that, you get this. So this is dx dx, which is 1. 1 plus dy dx squared. That's the arc length. And check it out. So you factor out a fourth, and then you got x to the fourth plus, instead of having minus 2, you get plus 2. And you're like, oh, well, that's obviously x squared plus 1 over x squared squared. Duh. And so the square root drops out, and then you can integrate it, and bam. This example is exactly the same as the one I've got covered up here in some regard. I mean, like we added 4 to make the minus 2 become a plus 2. This is kind of the same example algebraically, but it's either going to be something like this. It's going to be sine squared plus cosine squared, or it's just undoable, in which case the book probably has asked you find an integral solution. So listen, guys, we've covered most of the sections in chapter 10 except for the polar coordinate sections at this point. All right? So look at the homework. Ask me questions if you got them. Have a good weekend.